Welcome back to the second course in physics. Previously, we have discussed the evaluation of an electric field based on the definition of the electric field for a point charge, and then extending that into distributions of charges. And in this lecture, we will be tackling the problem using another methodology, the so-called Gauss law. So we'll consider Gauss law for the evaluation of distribution of charges and see some applications of this law. The contents of this lecture will include some introduction to the lecture, and then some definitions, basic definitions relevant to the topic, the flux of the electric field, Gauss law and the formulation of that, flux of a point charge, and then we will move on to the applications of Gauss law, and we will consider as applications problems having cylindrical symmetry, and then we will consider a problem with the planar symmetry, and then we will consider some examples on spherical symmetry. After that, hopefully we'll have time to discuss the differential form of Gauss law. In the beginning, let's mention that we have discussed the problems previously of the electric field arising from a point charge, and then we have extended that definition to the distribution of charges. And that definition was based on Coulomb's law. And we have noticed that from the definition, Coulomb's law does not use the symmetry of certain problems to simplify the problems. In some cases, the problem and the distribution of charges has a certain symmetry that makes it easy if we take into consideration the symmetrical argument of the problem. But Coulomb's law does not deal with that because it is concerned with the evaluation of the effect of a point charge. So a new formulation of Coulomb's law was derived by Carl Friedrich Gauss, who lived in the time between 1777 and 1855. He made a new formulation which would replace Coulomb's law in certain special cases of special symmetries. So Gauss law takes advantage of the special symmetry situation of the problem of the distribution of charges, and it encounters the construction of a hypothetical closed surface around the charge distribution. The surface is called Gaussian surface, and it can have any shape in general. But in order to simplify the problem, and that is the cause of Gauss law to begin with, in order to simplify the problem, we have to choose the surface to have the proper symmetry that goes with the symmetry of the charge distribution itself, meaning having the physical quantities that we measure over this surface to be constant, like the electric field. If we consider a surface where the electric field at all points of that surface is equal in magnitude, then that surface has a special simple symmetry that allows us to calculate the electric field in a simple manner. Gauss law as a formula is a mathematical relation between the electric fields at points on the Gaussian surface and the net charge enclosed within that surface. So that relation between the electric field, the magnitude of the electric field at the surface point, and the net charge enclosed within the surface, the closed surface, is the mathematical formula, the mathematical relation is the Gauss law. And now let's begin with the definition and evaluation of the flux, the electric flux, or the flux of the electric field, as a concept that is relevant to the problem in hand. The flux of the electric field is defined as follows. If we have a uniform field that crosses a plane of area A, then the flux through the area is defined by phi, that goes for the flux, is equal to the electric field, where the electric field is uniform, as we mentioned, dot A as a vector. Electric field is a vector quantity, and A, the area, is considered a vector where the magnitude is the magnitude of the area in square meters, and the direction of this vector A is the perpendicular to the area. That is, by definition, the direction of the area A. Since this definition is concerned with the electric field which is uniform over the plane, if we have a general surface of a general shape, arbitrary shape, where the electric field could be variable from one point to another, in order to calculate the flux through that surface, we divide this surface into small elements, extremely small, such that the field across each element could be considered as constant in magnitude and direction across each element. And then we can deal with each element separately. The flux across one of these elements, let's call it delta A, it has an area delta A magnitude, then accordingly the flux delta phi through that element of area is the vector E, the electric field in that area, which is considered fixed now, constant in magnitude and direction, times delta A, the area, and it's a dot product with the direction of the area, delta A, and the direction is n hat. That's a unit vector which is perpendicular to the area, delta A. In general, if we have a general shape, we take the area element, delta A, going to 0. In the limit of delta A going to 0, it becomes the differential dA, so small that goes to 0. And in order to calculate the flux over the surface, the whole surface, as we show by the figure, we make the integration of E dot dA, and we integrate over all the surface that we would like to evaluate the flux through. So in that sense, we can notice that the flux through the surface area is proportional to the number of the electric field lines passing through that surface, since the electric field strength E itself is proportional to the number of the electric field lines across the surface. And at this point, we are ready to define Gauss law, and we recall that the relation between the flux and the net charge enclosed in the Gaussian surface is the Gauss law, and this is stated as epsilon naught, the permittivity of free space, times phi, the flux through the closed surface, is equal to the charge, to the total charge enclosed within that Gaussian surface. This relation gives Gauss law, and it's a relation between the flux through a surface, a closed surface, and the charge enclosed within it. Thus, accordingly, if we replace phi by the formula that we can evaluate phi from, then epsilon naught times the integral of E dot dA evaluated over the closed Gaussian surface is equal to the enclosed charge within the surface. And so we can view this formula graphically as if we have a surface, a closed surface, we have a distribution of charges, we can construct a surface that encloses all of these charges, and the electric field is crossing this surface in any direction depending on the distribution of charges, and the total flux across this surface is multiplied by the permittivity of free space epsilon naught, if this is free space, of course. This should equal to the net charge enclosed within. So we add the charges, taking into consideration plus or minus, of course, we add it. And the net charge is the total flux multiplied by epsilon naught. And now we can apply these concepts and definitions to calculate the flux of a point charge, because it's the simplest distribution that we can have. That's the point charge. And if we consider a point charge, the simplest Gaussian surface that exploits the symmetry of the problem, the charge distribution, is a point. So the Gaussian surface that has the same symmetry of the charge distribution is simply a sphere, a spherical surface. The spherical surface has the symmetry of the point, and where the electric field over all the points of the sphere, the electric field has the same magnitude. It varies in direction, of course, but it has the same magnitude. And it's always, the electric field is always perpendicular to the surface. So the electric field is in the same direction of the area itself. So when we have E dot dA, the area direction and the electric field direction are in the same direction, and thus we arrive at a very simple formula to evaluate that does not include angles and some difficult mathematical terms that we should deal with. The electric field and the area are in the same direction, and the electric field has a constant magnitude. So taking these into consideration, the flux of the point charge across this spherical surface is E dot dA by definition, and we replace E by its value as Q over 4 pi epsilon naught R square times dA, and here E dot dA as vectors is equal to E as magnitude times dA as magnitude, because E and dA have the same direction. And this is simply, since Q and 4 pi epsilon naught R are constants for the spherical, over the spherical Gaussian surface, since R is the same constant also, then this is taken all outside the integral, and we are left with the integral over dA over the spherical Gaussian surface, and the integral over dA is simply A, which is the area of the spherical surface. And the area of the spherical surface is simply 4 pi times R square, where R is the radius of the spherical surface. Then that way we can notice that the flux is due to a point charge through the spherical Gaussian surface is simply Q divided by epsilon naught, which is the same relation dictated by Gauss' law. And this is exactly the same relation we have mentioned before, but here it is derived for a special case of a point charge. However, even though we have derived this relation for the special case of a point charge in the middle of a spherical Gaussian surface, this relation remains the same, exactly the same, even if the charge is not a point, and even if the surface is not spherical. the relation, which is Gauss law, is exactly the same, which correlates the flux with the charge enclosed within the Gaussian surface. And now, after we have defined Gauss law and the different terms related to it, let's move to some applications of Gauss law. And in order to apply Gauss law, we have to keep in mind that we should be dealing with symmetries, with simple symmetries. That's where Gauss law is applicable. For example, we deal with the very well-known and simple symmetries of, for example, cylindrical symmetry, which is linear symmetry, and planar symmetry, or spherical symmetry. Those are the three problems that we should be considering, and in most cases, Gauss law is applicable in, and it works beautifully in these three symmetry problems. In the case of cylindrical symmetry, for example, we ask ourselves, what are the charge distributions that have cylindrical symmetry? For one thing, a straight line, a charged straight line, an infinite line that is charged, has a cylindrical symmetry, because a cylinder where the line is coinciding with its axis, that cylindrical surface is a symmetrical surface around the line charge. So infinite line charge has a cylindrical symmetry. An infinitely long cylindrical shell that is charged also has cylindrical symmetry. It's like its shape. It looks cylindrical, like the cylindrical surface. And also, an infinitely long cylindrical solid cylinder, an infinitely long solid cylinder that is charged also has cylindrical symmetry. So we can apply Gauss law beautifully to these three problems using the cylindrical symmetry. And as an example, let's take the problem of evaluating the electric field near an infinite line charge. In the case of infinite line charge, we consider that the density, the linear density, is lambda in coulombs per meter, and we take a cylindrical surface around the line charge. And from symmetry, we notice that the electric field is perpendicular to the line. So it is perpendicular to the lateral surface of the cylinder. And of course, it is parallel to the surface. It is in the surface, in the upper surface and lower surface of the cylinder. The top and bottom surfaces of the cylinder, the electric field is in the plane, but it's perpendicular to the lateral plane. We notice that the electric field is perpendicular to the line simply because if we take two symmetrical elements above the line and below the line, these two symmetrical elements would have the same magnitude of electric field with the directions shown by this shape, by this figure. And the electric field can be decomposed into its components, the vertical component and the horizontal component. The vertical components cancel because they are equal and opposite in sign, and the horizontal components add up, resulting in the fact that E is perpendicular to the line. So everywhere around the line, the electric field is perpendicular to the line, thus perpendicular to the cylindrical surface. This is how it is. It has cylindrical symmetry. So at a point, a distance r from the infinitely line charged, the definition of Gauss law gives that the flux is equal to the Q enclosed inside the closed Gaussian surface divided by the permittivity of space epsilon naught. And considering that the surface is a cylindrical surface. Thus, the flux is the flux across or through the lateral cylindrical surface, which is 2 pi r times h, plus the flux across the top and the bottom of the cylinder. But the flux through the top and the bottom of the cylinder is equal to 0, simply because E is perpendicular to the direction of the area. So E dot dA is equal to 0 for the top and the bottom surfaces of the cylinder. So we are left with E times 2 pi r h. That's the total flux, which is the flux through the lateral surface area, and that is equal to Q, which is simply lambda times h, the density, the linear density times the length, which is h, which is the height of the cylinder, divided by epsilon naught. That's the charge enclosed within the Gaussian surface. And this relation leads to the result, finally, that E is equal to lambda over 2 pi epsilon naught r. That is the electric field at a distance r from the line charge. And now we consider the second problem with cylindrical symmetry, which is a uniform cylindrical surface. A uniform cylindrical surface with uniform charge density sigma. That is, the charge is on the cylindrical surface only, on the outside of the cylindrical surface. In the case, if we are interested in calculating the field outside the cylinder, that is at a distance small r larger than the radius capital R of the cylinder, that's at points outside, then we apply the same principles as before. We take a cylindrical Gaussian surface around the spherical shell, around the cylindrical shell, and the total electric flux is E times 2 pi times small r times h, which is the flux across the lateral cylindrical surface only, and the top and the bottom surfaces, they have 0 flux across them. That is equal to the charge inside the Gaussian surface. The charge inside the Gaussian surface is simply the density sigma times the area, and the area of the charge distribution is 2 pi times capital R times h, and that all divided by epsilon naught. That's from the definition of Gauss law. And then we get E is equal to simply sigma times capital R, which is the radius of the cylindrical shell, divided by epsilon naught r. A small r is the position at where we are interested in calculating the electric field. And if we replace sigma by lambda, because we have a cylindrical shell, we can either look at the charge distribution either as surface charge distribution per unit area, or as linear charge distribution per unit length of the cylinder itself. So sigma times 2 pi r h is the same as lambda times h. Lambda is the linear density in this case. So if we divide by 2 pi capital R, this area divided by 2 pi capital R, then sigma divided by 2 pi capital R, that is equal to lambda, and E is equal to lambda over 2 pi epsilon naught r. And this is the same result as for the infinite line charge. And this is the demonstration that if we have a cylindrical symmetry, regardless where the charge is distributed over a cylinder or a line, a big cylinder or a small cylinder, as far as we have the same symmetry of the charge distribution, the electric field at a certain point set up by this charge distribution, as far as it has the same linear density and the same shape, the same symmetry, it sets up exactly the same field, exactly, regardless of whether it is a line charge or a spherical shell. And we will see also if it is even a solid cylinder with a charge distributed within it, we will get the same results. E inside the spherical shell is certainly equals to 0. Why? Because the charge, if we take a Gaussian surface inside the cylindrical shell, the charge within this Gaussian surface is 0 because the charge is on the outer surface of the cylinder. So accordingly, the electric field inside is 0. And if we plot the electric field due to a cylindrical shell, a charged cylindrical shell, it looks like this, where the electric field is 0 until we reach the radius of the cylindrical shell, the charged cylindrical shell. After that, the electric field goes monotonically as 1 over r. It decreases as 1 over r. And now we look into the third problem, which is the long solid cylinder. And in this case, if we have a uniform density of ρ, and if we would like to calculate the electric field outside that long cylinder, it's an infinitely long cylinder, we do the same thing and we construct the Gaussian surface, the cylindrical Gaussian surface, and the flux through that Gaussian surface, E times 2 pi small r h, is equal to the charge enclosed, which is ρ times pi r squared times h. That's the volume, of the charge enclosed within the Gaussian surface, divided by epsilon naught. And this gives the electric field as ρ times r squared over 2 epsilon naught r. If we replace, because this is just a cylinder, if we replace the volume density by a linear density, which means that we consider that ρ times pi r squared is equal to lambda. Multiply ρ by the cross-sectional area, we get the linear density. Then this gives E is equal to lambda over 2 pi epsilon naught r, which is again the same result for the line charge. So we are getting exactly the same result outside. If we have a cylindrical symmetry, the electric field outside the distribution of the charge is exactly the same, whether we have line, cylindrical shell, or solid cylinder. However, inside the story is a little bit different, since now the flux E times 2 pi r h is equal to ρ times the charge enclosed. The charge enclosed now is not the total charge because the Gaussian surface is inside, so it takes part of the charge. Ρ times pi small r squared at this time times h over epsilon naught, and then this will give E is equal to ρ over 2 pi epsilon naught r, which is linear in r, which makes sense because as we go more in r, then there is more charge enclosed in the Gaussian surface until we reach, of course, the radius of the cylinder itself. And if we plot these results, we will notice that inside the cylinder, the electric field is proportional, linearly proportional to r, because we are increasing charge as we increase the distance or the Gaussian surface radius. And then outside the cylinder, the electric field goes as 1 over r, which is similar to the line charge. And now we consider a second symmetry type, which is the planar symmetry of a charge distribution. And in this case, we consider the electric field near an infinite plane that is charged. Consider that the plane is not non-conducting plane where the charge can be set anywhere on the plane. And consider that we have a uniform charge density sigma per unit area. Then we can construct a small Gaussian surface that encloses part of that charged area. And here the small surface, closed surface, is considered a cylindrical surface for simplicity. It can be any shape. It can be cubical, for example, if you wish. It doesn't matter. It gets the same result. This is an illustration. Notice that the electric field is going in the two opposite directions, and notice also that the areas on the top and the bottom of the cylinder are in the direction of the electric field, while the lateral area of the cylinder is actually perpendicular to the electric field. Thus, there is no flux through the lateral area, but the total flux is through the top and the bottom, each one of them of area A, we consider it. Thus, the flux is the flux through the first area, the one to the left, which is simply EA, and plus the flux through the right-hand side area of the closed surface, which is again another EA. So the total flux is 2 EA, and that is equal to the charge enclosed, which is the area enclosed, which is simply A, times sigma over epsilon naught. And that gives the result E is equal to sigma over 2 epsilon naught. So this simple relation, sigma over 2 epsilon naught, gives the electric field near a plane that is charged with a charge density sigma. Of course, although this is considered an infinite, but everything is relative, what do we mean by infinite? We mean that the surface not necessarily has infinite dimensionality, but at least if we consider even a page from the book, if it is charged, if we consider distances that are very close to the page itself, then the page looks like infinite relative to the distance to the point we are calculating the electric field. So this formula applies for any shape of the surface if we are calculating the electric field near the surface. This formula, sigma over 2 epsilon naught, still gives the electric field near the surface, regardless of the shape of the surface. Unless, of course, if it's pointed or something. Now, the third type is the spherical symmetry. And in spherical symmetry, we ask ourselves, what are the problems which have spherical symmetry? One of them, the simplest, is the point charge, where the point charge is at the center of a sphere, so it has spherical symmetry. Also, as a spherical shell has a spherical symmetry, or a solid sphere itself has spherical symmetry. So a sphere or a spherical shell or a point charge, all of them have spherical symmetries. So in that case, we can apply Gauss law, considering or constructing a spherical Gaussian surface that coincides with the spherical distribution of charge. And for a point charge, for example, we construct a spherical surface around it, and the electric field is constant in magnitude over the spherical surface, and the flux is E times 4 pi r squared, which is the area of the spherical Gaussian surface, is equal to the charge inside, which is Q, the point charge, simply, divided by epsilon naught. And that gives the result E is equal to Q over 4 pi epsilon naught r squared. This result has been obtained several times in several different ways, from Coulomb's law, from the definition of the electric field, and we have observed this relation in several occasions. It's the same thing. And now we consider a spherical shell. If we consider that the spherical shell is charged uniformly by a surface charge density sigma, then if we want to calculate the electric field is different from outside and inside the shell. So outside the shell, we anticipate that the electric field should look like exactly like the electric field due to a point charge. It should, because it has exactly the same the same symmetry. So E outside, we calculated by E times 4 pi epsilon, 4 pi r squared, which is the flux, and that is equal to the charge within the Gaussian surface, which is sigma times 4 pi capital R squared, that's the total charge, divided by epsilon naught. And that gives E is equal to sigma R capital R squared over epsilon naught R small r squared. And now if we replace sigma by the charge Q, the total charge Q on the sphere, sigma times 4 pi r squared is the total charge on the sphere. So if we multiply by 4 pi r squared over and above in the numerator and denominator, we reach E is equal to Q over 4 pi epsilon naught small r square, which is the same as for the point charge. You can convince yourself of this result. And the electric field inside the spherical shell is equal to 0. That's because we don't have any charge inside. And since the charge inside is 0, then the electric field is 0. And this is also consistent with the previous argument that if we put a point charge inside a shell that is charged, then the charged shell does not exert any force on that point charge inside it. This is consistent. There is no electric field. That means there is no force inside. So if you put any point charge inside a charged shell, it will experience absolutely no force, which is consistent with our previous argument. And if we plot the electric field due to a shell, it looks like this. Inside it is 0, and then outside it goes like 1 over r square, which is like the electric field set up by a point charge. It's the same formula. And for a solid sphere, we assume that we have a uniform density ρ, for simplicity of course, a uniform density ρ, and the electric field outside also we can anticipate that it is exactly the same as for the point charge, where Q is the total charge on the sphere. Let's calculate it. In this case, E times the surface area of the Gaussian surface, 4 pi small r squared, is equal to the total charge enclosed, which is the density ρ times the volume of the sphere, of the spherical, of the charged sphere, 4 over 3 pi capital R square over epsilon naught. That's Gauss law. And this will give E is equal to ρ times capital R cube over 3 epsilon naught R square. Now, if we multiply over and above in the numerator and denominator, if we multiply by 4/3 pi r cube, which is if we multiply by 4 pi, 4 over 3 pi, and we recognize that 4 over 3 pi r cube times ρ is equal to the total charge, then we arrive at exactly the same formula E for a point charge. And E inside is a different story because we have charge inside now. In this case, we construct Gaussian surface inside, and the flux E times equals E times 4 pi small r squared is equal to the total charge enclosed. This time it is ρ times 4/3 pi small r cube over epsilon naught. And in this case, the electric field is linear. It is increasing with r because as we increase r, we increase the charge enclosed until we reach, of course, the radius of the sphere. And the plot of the electric field set up by a charged solid sphere is like this, where it goes linear until we reach the radius of the sphere itself. And then after that, it goes like 1 over r squared, like in the case of the point charge. This is consistent with the previous argument. And now let's look into the differential form of Gauss law, because we have looked at the integral form of Gauss law before. And in order to arrive at the differential form, we make some definitions, and we consider a volume element, and we consider that volume element to be cubical, with the volume d tau equals dx times dy times dz. It's cubical in shape, and that cube contains a charge dq inside it. Now, we calculate the flux through the 6 sides of the cube, and we calculate the flux across each side one by one. For example, the flux that is set up due to the z component is the flux through the top and bottom surfaces, and that flux, we call it d phi z, which is due to dEz, is simply E in the bottom part times the area, which is dx dy, minus the flux on the top part, Ez on the top, times the area of the top dx dy, minus the electric field Ez in the bottom times the area, which is also dx dy. So the result is the difference between the electric field on the top and the bottom. And if these are considered so close to each other, the difference in the electric field is simply dE, delta E, which goes to dE as we go, because the difference is so small between them, because the distance is so small. So d phi is simply dE times the area dx dy, or we can multiply and divide by dz, and this will give us dEz by dz times dz dx dy. dz dx dy is simply d tau. And this will give us d phi due to the z component is equal to dE by dz times the volume element d tau. Similarly, we evaluate the flux due to Ey and to Ex, and we reach similar conclusions that the flux due to Ex is simply dEx by dx times the volume element, and d phi y is equal to dEy by dy times the volume element d tau. So the total flux through all the surfaces is simply the charge, which is dq over epsilon naught, which is the summation of all the fluxes dex by dx, dEy by dy, dEz by dz times d tau. And this notice that dq by d tau is equal to rho, the density. And if we define the gradient operator as d by dx I hat, d by dy j hat, d by dz k hat, we reach the result that gradient dot E, which is div E, is equal to rho over epsilon naught, and that is the differential form of Gauss law. And at this point, I would like to finish this lecture. Thank you.